In this video, I want to present the method of cofactor expansion. This is a method of calculating determinants that uses this determinant formula that I've referenced before that we don't really want to apply directly, but it uses it in an iterative manner. And it makes it so that you don't really have to keep track of whether you're actually picking all ways to choose exactly one entry from each row and column. And you don't really have to keep track of when you're supposed to put a -1 there. So that's what cofactor expansion does. I'll revisit that after I give an example when I go through the why this works section, where I'll hopefully convince you that that's what we've accomplished. And in particular, cofactor expansion is useful when you have a matrix that contains a lot of zeros. And in practice, in application, not always, but this is often the case. That is that whatever application you're doing, you expect lots of zeros, and cofactor expansion might be a great way to calculate a determinant that would be much faster than something else. So in order to present this method, I want to get to the example as quickly as possible, but I do need some terminology and some notation. So we have this idea of the ijth minor of a matrix. And it's the determinant of the matrix that you obtain by removing row I and column j from a matrix. So let's quickly get into an example because this sounds weird. What I'm saying is that if I want, this is my matrix B, and if I want the 2, 3 minor of this matrix, what I'm going to do is I'm going to remove row 2 and column 3 from this matrix and take the determinant of what's left. Now, when you remove a row and column, you've removed equal amounts of things in rows and columns, so you do end up with a square matrix. And so I want the determinant of the matrix 3, 6, minus 1, minus 1, which is 3 times minus 1 minus 6 times minus 1, which is 3. So for this matrix, the 2/3 minor is 3. So a minor of a matrix is ultimately a number. It's a determinant of kind of a submatrix determined by removing a certain row and a certain column. I want to have another term related to this. We're kind of building this up slowly. I'm going to want to incorporate plus and minuses in order to apply this formula iteratively. And we have this idea of the ijth cofactor of a matrix, which is it's similar to the minor, but we also multiply by -1, or maybe we don't. So in this example, C sub 2, 3 is -1 to the 2 plus 3 times M sub 2, 3. So it's -1 times 3, which is -3. And so these cofactors are going to allow us to multiply by -1 or not, kind of in the way that the formula needs us to. Okay, we have all of our terminology. I want to get to the example where I'm going to use cofactor expansion to calculate the determinant of a matrix. So here's my matrix, and I want to use cofactor expansion to calculate this determinant. I've written two formulas down here that look, I think, kind of crazy, but I'll apply each of them. I'll only work through the full calculation for one of them, and hopefully you'll understand what they mean. So here's the formula for cofactor expansion along a row, and here's the formula for cofactor expansion along a column. And it's saying that we can figure out the determinant of this matrix in terms of its cofactors and the corresponding entries along a fixed row or a fixed column. The idea of cofactor expansion is that we're going to take advantage of zeros in the matrix. And so I want to choose a row or a column that has a lot of zeros in it. And I have multiple choices here because the rows and several rows and columns have 2 zeros in them. I am just going to choose, because there's no better choice than another, row 4. So I'm going to do cofactor expansion along row 4. And after I work this all the way out, I'll set up what would have happened if I did cofactor expansion along some column. So I'm choosing row 4 because it has maximum possible zeros. 2. What does this formula say? This formula says that if I want to figure out the determinant of A, I'm working along row 4 here. I'm going to go from left to right across this row. And this is going to be equal to A sub 41, C41, plus A42, C42, plus A43, C43, plus A44, C44. And let's get this all on the same screen. A41 is this entry 8. What's C41? C41, well, we have our -1 term to the 4 plus 1. And then we have the minor of the matrix. And that minor, the 4 first minor, is what I get rid of when I get rid of row 4 and column 1. So it's the determinant of this matrix. So this, what I've written down, is this whole first term. And I think this may look kind of intimidating, and that's fine. It kind of is. But we'll see it's not so bad in the end as we work through this. All right, what's our next term? A42 is the 0. And I should write this out, but I know what's going to happen. I'm going to save myself some time. Yeah, it's 0 times something that looks like this. But I'm not going to worry about what that thing is because it's going to disappear. What's my next term? My next term is A43 times C43. So A43 is this 1. I'll scroll back up when I need to. And I get -1 to the 4 plus 3. And now I get the minor, the 4-3 minor. So it's the determinant of this matrix, 1, 5, 2, 2, 7, 6, 0, minus 1, 5. And now I move along. My fourth term, A44 is 0. And again, I'm not going to worry about what else happens. Whatever this ends up being, it's going to get multiplied by 0. So I've written out my whole cofactor expansion formula with this added detail that anytime my entry is 0, I'm not going to write out all that stuff. Right? You could actually just leave it out, but I wanted to make it clear why this thing's being omitted. Okay, so let's clean this up a little bit. So I have 8 times -1, which is -8, times this determinant. And similarly, I get a -1 times this determinant. Okay. So as I move along, I think this is a useful technique in general. Organizing work can get challenging when computations get complicated. And one thing that I really like to do is to do what I call side calculations. And so what I mean is I'm not going to try to keep working with this. You could. That is, I could try to figure out what this determinant is within this separate calculation. I think there's no point, though. I'm going to come back to this later, but for now I want to separately figure out what are each of these determinants? And I realized I wanted an example of cofactor expansion on a column, and so we're going to get to do one here. So I actually won't have to come back and give a second example. I want to figure out what the determinant of this first matrix is, and this matrix contains a lot of zeros. And in particular, I see a column with 2 zeros, and I'm going to cofactor expand along that column. I'm just looking at this matrix. I'm not thinking about the -8 or the fact that I'm eventually going to subtract something else from this. All right, so I'm going to cofactor expand along column 2 because it has a couple zeros. And what I realize is, as I move down, so I take the first entry, that's a 0. I'm not going to worry about what's there because it'll become 0. I take the second entry, that's a 3. Now, the formula for cofactor expansion along a column is the same as the formula for a row. I'm just going along a column. And so I'm going to multiply my entry times the cofactor. And remember, the cofactor is just maybe a -1 times the minor. And so I get -1. This is entry 2, 2. So the 2 plus 2 times the 2, 2 minor, which is what we get when we get rid of row and column 2. So 2, 0, 6, 5. And then when I get to the third entry, again, that's a 0. So I don't need to worry about what actually happens with the cofactor. And so here I get 3 times the determinant of this matrix. And I guess I could cofactor expand, but when I get to a 2 by 2 matrix, I have a nice formula for it. This is 2 times 5 minus 0 times 6. And so I get 30. So as a side calculation, I figured out that this matrix is 30. Sorry, the determinant of this matrix is 30. We're going to do the same thing with this matrix. And I guess I should point out, if you really don't want to see me calculate that determinant, you could skip ahead, right? You can find where I go further, but you could also just pause it, try to solve it yourself. So how am I going to find the determinant of that matrix? 1, 5, 2, 2, 7, 6, 0, minus 1, 5. Let's just copy it so I don't get it wrong. One of the nice things about doing it this way is I could do this however I wanted, right? I could find this determinant, even though I'm doing a cofactor expansion. I could look at this and say, well, it doesn't have that many zeros, right? There's only 1 0. I could just do this determinant using row operations, for instance, but I'll decide not to. I'll do cofactor expansion on row 1 because it has a 0 in it, so I'm getting something out of that. And I'll be a little quicker here because I've already done a few of these. It's 1 times maybe -1 times the minor. Plus 2 times maybe -1 times the minor. And I'm not going to write out the third term this time, right? The 0 is going to disappear. Now, this whole first part is just 1, and so I get just this determinant, 7 times 5 minus -1 times 6. And then I get -2 times 5 minus -1 times 2. 35 plus 6 is 41. 25 plus 2 is 27. And so I get -13. I'm done with my side calculations. And so this is where I'll copy and paste it so we have it in front of us. Right, this was, I guess, let's let's draw it like this. All of this stuff was off to the side. I was just doing this in service of this later calculation. And I just want to continue with this. It's going to be mad at me because of how I did this. Just copy this. Paste it here. And so I found that this determinant was 30. And I found that this determinant was negative 13. And I get that the determinant of this matrix is negative 227. That is the determinant of A. This matrix up here is negative 227. So a quick refresh, I can cofactor expand along rows and or columns. The idea is that I look for a row or column that has a maximal number of zeros. You don't have to, it just saves you a bunch of time because the zeros work nicely. And I work out how this cofactor expansion formula applies as I move along the row or column. And notice when I get these resulting determinants, I go and calculate them separately, right? I don't try to keep one formula going. That's a really poor choice. The one exception being once I get down to 2 by 2 determinants, those are straightforward to apply the formula to. I don't need to create some other separate side calculation. And so in the end, I work all the way down to this determinant being negative 227. So I'm done with the calculation. I wanted to give a brief why this works explanation. And specifically, I wanted to explain what do I mean when I say that we're really just applying this formula. The idea is, let's just say we're cofactor expanding along a row, because that's what we did to start. We started by cofactor expanding along row 4. This formula tells us we need to figure out all of the ways to pick exactly one entry from each row and column. And we might need to multiply that by a -1 according to a rule that I've never told you. What the cofactor expansion formula is doing, here we're saying, look, well, let's just start by, if we have to pick one entry from each row and column, let's start by figuring out which entry we're picking from row 4. Right? I could either pick 8 or 0 or 1 or this other 0. And now once I've picked, for instance, 8, my remaining choices, if I can't pick something else from that row or that column, are given by here, which is why we're considering that minor. And I now have to pick one entry from each row and column of this smaller matrix, which again corresponds to the determinant. And so that's the picking one entry from each row and column. And then the negative thing, again, I never really gave you a rule for this, but the whole idea here is that we're keeping track of whether there needs to be a -1 at each level, right? So this choice of 8, say, okay, well, because I chose that entry, I do need to put a -1 here. But then later on, when I'm calculating this determinant, another combination of my combination of choices of entries, I might introduce another -1 and cancel that out, or maybe not. So that's why this works. It's just an iterative way of going through the matrix and selecting an entry from each row and column and maybe multiplying by -1. And in particular, it takes advantage of situations where you have a lot of zeros, because you quickly identify that if this is the entry that you pick from row 4, you don't need to worry about anything else because it's all going to multiply out to 0. So hopefully that clarifies a little bit of why this formula works. And again, it can be a really quick formula if you have a matrix that has a lot of zeros, especially if they're all in the same row or column.